Okay, so let's go on to hopefully the last thing we're going to look at in this piece of code. So all we're going to do is we're going to rework this part so that we can do our menu selection. And so I think the big thing that we have that we could take advantage of here is the fact that we're using the number keys and they're all right next to each other. So we could move this dice up to the top, right? Because things that call dice are clear and quit, which both basically reset the whole thing. And that's fine. Okay, this label though really bugs me. More than anything else, this label bugs me. So this is label A, and it's really though the place where we go to read in a character. So let's call it getChar. So we're going to call it getKey. And so now this is local to dice. So we have to change all of dice's symbols to being local, otherwise, right? It's not going to think. Well, let's test it. Label A is here. Let's call label A dot get key, and this isn't going to work because it's going to say there's no get key in check t. It's in dice. That's a different function. Let's see. So if I get, so we made that change. So let's make it. And we get an error, right? It's looking for a check t get key. That's no good. We can just change all of these. But conversely, we're just going to change all of this while we're here, because we're not going to intermediate change this stuff anymore. In fact, we're going to reorder this in a huge way. So we're going to check for the letters first, and then if we don't get the letters, we're going to assume they meant it to be a number, and then if it's not the numbers 1 to 7, then we're going to just get rid of it. So we do that. So this would be, we're just going to maintain a little bit of the illusion here. This guy wouldn't go to continue. This would go to check 1. And this guy wouldn't go to check Q. He'd go to continue. So we've now reordered this. And so, because as you can see, this is a lot of jumps, right? Like there's no way to maneuver through this list. It literally either jumps back or forward. That's just dumb. So yeah, if it's Q, this would be the end program, but instead it's going to be, do we want to put a end program block that we could then replace if things go bad? What we could do is have, if it's a Q, we call return and then have our starting program call dice. Yeah, so we're going to clean this up a ton. We're going to make an init function where we start. And so init is going to put us into text mode. So this is going to seed the random number generator and clear the screen. Sorry, not clear the screen. This is really go to text mode. So then now we could actually use one of those clear screen ints that we saw before. In int10, right character teletype, right character string, scroll window down. We're going to have to experiment with this. So we'll do that after this. So for now, we're going to have this clear screen use this guy. We might have to change that. So then the last thing int is going to do is it's going to call, this is actually, we're going to have a local variable here called main. So this is going to call dice, which will call into the dice program. Jump back to main. So now we have sort of a setup program. And now if we wanted to, we could put all of our data up here, and that will reduce our number of passes. But not significantly, because we still have to do 2 passes, because this call to dice is going to be a jump down. So we'll leave it where it is. So now this is a main. So now if you hit the Q key, what it returns. If we're going to put the C up here. We're going to call this not Q. We don't have to call this check Q anymore. Instead, we're going to do them this way. Return, and then we can do not Q. This was a very minimal change in terms of the final program, but it's much clearer, I think, already. Because now this is what do we do, and then this is just basically an else of it being not Q. Right? But now we should put a comment here that's like case Q. And if it's not Q, and we're going to use a little more white space now to get us a little more room. So now we're going to do if it's equal. If it's equal, we're going to jump back to dice. So this is case C. Restart dice. That says it's a jump. Because then if that doesn't work, then we're going to, this is now, by definition, not C. So now we have case T. And if that's not equal to that, then this is, we're going to jump to, oh, I forgot the dot up here. Not Q, not T. So not T, it's going to bring us down here. Not T. Otherwise, it's going to print the dashes and then display total and then go and get the next instruction. So now if it's not T, what we're going to do is we're going to subtract 31 from it. Because that way we'll just have a quick lookup. Right? So if it's if we subtract 31 from it, if it's 0, we want 4, 1, 6, 2, 3, 4, 5, 6. So then if it's 7 or more, it's bad. If it's less than 0, it's bad. Also, we're doing this as a unsigned comparison, so it should make all illegal values greater than 7. So let's do that. So first we subtract from AL 31 hex. AL equal AL minus character 1. I like to try to use C for comments in here. So, and we can actually do that like this. Right? So, just like we used those strings up there, actually let's use the double quotes, because so that should now subtract 31 from it. So now we can, let's create a list of dice. So dice, these are words. So we could save memory and store them in bytes. Yeah, we're going to save memory, store them in bytes, and then we'll load the high word with a 0 and the low word out of this list. So it's just 4, 6, 8, 10, 12, 20, 100. And that's it. So we can't call it dice though. So we're going to call it options. Because die is already taken. And dice is the name of this routine here. We could like call it dice with a different capitalization, but I think I'd rather not, I'll just say. So now we just got to compare AL to 7. Compare AL to 7. And if it's less than 7, we're good to go. If it's more than 7, it's an invalid entry. So jump greater than or equal to. We can go back to get key. And we're just going to ignore that key that they pressed. So this is now going to make it so you can't just mash keys when it starts up and get dice from any value. It only will accept valid commands. So one nice thing about the way this used to work is you could, after you picked a die, you could hit spacebar to get it to roll the same die again. But I think in practice, I can always bring that back later. So all we need to do is we need to save the value that's in AL. And then we can use it here when we use die. And that actually lets us change this one. Right, because die is used in all of these places for access, but we're going to get rid of all of them. Yeah, let's do this. Let's get rid of die. This is the die we're rolling. This guy uses BX. CX isn't used anywhere in here. So we could just dump it into CX. And then... so this is a byte. So we can do... multiply... Oh. We need it to be a word to do the multiply. And we could do it the word from memory and just, I can make this, but we don't want to waste, let's try to not waste the bits. I know it's just like, a couple bytes, but the part of the whole reason we're refactoring this is try to get that down. So BX is only used for this division operation. This could be BX or CX. Our offset couldn't be AX. I think BX was okay though. So we can use BX. What we really want to do is we want to extend AL into BX. And I know there's an instruction for doing that. It might even just be move. Load. Move. Let's try move. So after get key, we want to move. And if this is wrong, we can fix it later. We're going to move into CX, AL, and then we don't need this anymore, any of this. That's a lot lighter. I don't think continue actually comes into play anywhere now. So maybe we could try just word die plus, oh no, but it's a byte. It's a byte. So we're going to move into BX, byte, die, plus CX. I might even be able to just do die plus CL. Probably not. Okay, so this is going to do our lookup. So this is bx equal. So this is doing the same thing though, where we have we're taking a byte and putting it into a 16-bit register. We might have to zero it first, or zero the high byte and then load the low byte. Bx equal. This is really like die sub key minus 1. So we're taking the key value, which is what we read into here. We subtract 1 from it, index that into our array, read that into bx. So then this is just times bx. Okay, word die multiply max rand div increment. Yep, so we should be, oh, this label A is now dot get key. So this will then flow through and go all the way back up to get key, which will get the next key. So let's see if that worked. As I said, I'm almost certain I have to do something to sign us in that manually. Yep, operand sizes do not match. We got that warning before, which means I've done it before. So I assume it was the AL to CX that gave us a problem. So we're just going to use CL, and we'll 0. So we'll use an XOR to do that. Oops, CH. Let's see if that works. Okay, so that got through that one. So this is just like an alternate way to zero a register. It's actually, I think, faster, or so I've been told. Let's take a real quick look at XOR. So XOR takes a register is 3 clocks. Move register immediate is 4 clocks. So it does save you a whole clock. So we could have, but now you have to comment it. So we're just going to do CX equal AL. So this is just saying we're setting CX to the high byte 0, low byte AL. And then, I wonder, if we do BL here, I've changed this guy from CX to CL. Does that work? Because then we could save ourselves a reserve word, use this symbol. Okay, so CX. We're going to move that into BL. CX is not an option. Does it have to be BX? Does that mean? It's not that big a deal. I think we can just swap where we use CX and BX here. Right, because this guy can be CX. Let's take this instruction out here for the time being. Yeah, so that would build. So, sure. Well, this guy be CX. And we'll have this guy be BX. Actually, we could do all the processing we have to up top there to get CX to be the dice. That way we do all that at once. Yeah, so we're going to move this guy to... Yeah, so we're going to multiply by BX. We could actually have left these guys BX then. Because BX isn't going to get modified by anyone else in here. And the big change here is BX is going to be dice. So we're just going to say up here AL is key minus 1. I don't want to have more moves than we absolutely have to. And this is like if key minus 1 is greater than or equal to 7. Get next key. We're going to roundabout set bx to die sub key minus 1, but the first thing we have to do is move al as key minus 1. So we move that into bx. Thusly, then we can move that into BL. So the low value goes from being the key minus 1, and then here we're reading that byte value out of there and putting that into the low byte, but the high byte's still going to have been zeroed here, so there's no reason why that would have changed. So then bx will be die key minus 1. Bx equal key minus 1, and then bx equal die of key minus 1. So theoretically now this will build and give us the program we all want. So you can see we went from 130 being down here to up here. And if we could probably fish 4 more bytes out of this, and then it would be less than 256 bytes. But that's half the memory we need. But you can see here, though, is our D4, D6, D8, D10, D12, D14. No, that's hex. So 16 and 64, which is 6 times 16 plus 4, which is 100. Yep, let's make run it. Okay, so let's try some D4s. Those look like D4s. Total looks good. 2. Oh, there we go. There's some 6s. Clear works. Let's try D8s. See some 8s, see some 1s. See a total. Clear. D10s. I see some 10. I see a 10. And I see a 1. Oh, I started to hit 5 instead of 4. So it's a 10. There's a 1. Looks good. Go to 6. Now I'm doing 6. There's a 20. Haven't seen a 1 yet. There's another 20. There's a 1. 3 20s in the time it took to get a 1. So let's do D12s. So there's a 12. Another 12. 11, 10. There's a 1. I'm not going to roll D100s until I get 100 and a 1, but I'll... Whoops, wrong button. I will roll until I get something over 20. Oh, what do you know? I got stuff over 20. Now when I quit, it's basically the same as clear. But we know internally it's different, because now quit goes to, literally we're returning from our main function back to our init state, which then says, nope, you never leave your main function, and calls it again. Whereas if you clear it, all we're doing is resetting that thing. So let's experiment with that on the topic of clearing. We're going to wrap this guy up here. So you'll see now we replaced all of those symbols with now just 3 local symbols. And a little bit of arithmetic to remove a ton of conditionals. And those conditionals can really, right, like, and all of them were take the alternate path conditionals too, so you know that they were, that had to be getting expensive. Not, once again, this is an incredibly simple program, so it doesn't need that much processing power. I mean, this you could probably run this on like an original IBM PC and be like, yep, it works exactly as expected. So let's look at E10. So I think we want scroll window up. Scroll a specified window upward a specific number of lines. Number of lines to scroll. If 0, clear entire window. It'd be great if there was something that spelled this out a little bit more. Let's look for, so we want to find something on int10.6 or int10.7 that's look at this guy's code. 7 for background. Starting coordinates, ending coordinates. Oh, I see. It says it's like it goes from 0, 0 to what was that? 16, 24. Yeah, so 0 to 24. This is probably 80. It's actually 79, but yeah. So 24, 79. So plus a 0. This expresses a lot of information that wasn't in that other document, right? I mean, the other document did say the coordinates, but it did have these attributes that I was very curious about. And that's probably where our problems were coming in. So, yeah, this is going to add a couple bytes to our program, but that's fine. We'll clear the screen the correct way. Clear the screen. So we move that. We move into, what was it, BH? Yeah. BH. 71. Move into CX. 0. So start at 0, 0. DX, comma. We want to go to 24. So we want to go to 18 4F. So I feel like we can play around with this. We might be able to maybe get some text colors in there if we play with those, but we'll these maybe some shades of gray. 24, 79. Go to text mode. That will might as well. There it is, 25 by 80. You know, I should really do this the other way around. We'll do it XY. I mean, there's not a lot of reason to think this isn't going to work. Ugh. It looks like... So let's change one of these and see if I hit clear. So it's actually not resetting the cursor position. Clearing the screen, but not resetting the TTY. I wonder if there's probably a way to manually move the cursor. Let's look at those. Set cursor position. Row column. So we're going to manually do that too. Now, I'm very quickly saying that this is definitely not more efficient than just telling it to go to text mode. Right? Like, we don't need this to be lightning fast. And this is a lot of code. But I'm here. I'm going to play around. So, which one was that? That was 2. And BH needs to be 0. And D is row and column. BH needs to be 0. We don't care what CX is, but DX. Row column 2. Do we care about AL? Nope. Let's try that now. Okay, That looks pretty good. And if we roll some dice, let's roll some die 100s there. Ooh, 100 off the bat. Not bad. Clear it. There we go. That looks much better. If I hit junk characters, it doesn't do anything. Ooh, interesting. The spacebar is giving me 1s. Backspace gives me 1s as well. It's doing a signed comparison on our... We didn't verify that before. Back at the ASCII table. Right, so we were looking at stuff here. And so we said subtract 30. And then if we treated it as an unsigned number, we would have been fine. But because it was treating it as signed, these numbers are going to all be valid. So we need to do an unsigned comparison so that only these values stay valid. See space over here. I wonder what the backspace character says. Like, oh, there it is. Control H. I was gonna say, isn't it like a Control H? So, fun little factoid. Just like, so right, if you start here and you hit Shift, it puts you in this column approximately, right? Like, you get your uppercase letters. If you look around the keyboard, you'll sometimes see there's actually like a similar relationship here. Right? There's a character that does the sort of opposite. Right? There's a key that's a slash and a pipe. Square bracket and angle brackets are also in the opposite direction. So there's like sort of a shift relationship between these two columns. Well, between... I mean, you could maybe see it as a if you had caps lock on, you'd be in this one, and then if you hit shift, you'd always go over to here. Except for at doesn't go to, there isn't an at key. But there are keys for these, and they go to this when you shift them. And caret, there's not a caret key. And there's not an underscore key? No. But so that's a but then control sort of brings you back to this column here. So control C is end of text, which is the character that basically causes the program to fail. It says, "Oh, there's no more input. I'm gonna stop." It's sort of like end of file, but not quite, but similar. A lot of these control characters are dubiously used, but one you do see a lot is some things use Control H for backspace. The other option is Control question mark, which doesn't, get you anywhere. Because in practice, people use scan codes and stuff to do this, but this is sort of just a little bit of the way ASCII sort of maps to things. Matter of fact, because you can hit like Control, right, like 10 is line feed. So you can sometimes get one from a Control J. Let's see if we go to here. Let's well, yeah, I can just hit some control characters. So if I hit Control C, that sends an invalid entry. And if I could set a control, or I can hit Control on anything. If I just hit the letters, nothing happens. But if I control on a letter, we get one of those control characters. I'm back here, though. Yeah, nah, the window. Whoa! Let's close our window. That's sad. Here. Yeah, be careful mashing control characters, because when the window manager catches them, it does stuff like that. So, we need this comparison. Jump greater than or equal to. So we want this comparison to be a unsigned comparison. Jump if above. Yeah, okay. So jump above. So is there a jump above equal? Okay. So jump above is what we need. It is the unsigned version. So let's see what happens if we do that one. Awesome die 20s here. Total those up. Hit clear. Not good. Let's hit some backspaces. Spaces. There we go. Now we're getting what we expect. Nothing works. Total works. Clear works. It is faster. So before, when I'd hit quit, I don't know if you could see this, it had like a little lag as it almost looked like it was changing video modes, you know? Which makes sense. So maybe this is worth going with. Plus we can choose a nice color then. So let's cycle through our background color, shall we? We'll leave this foreground color blue. Matter of fact, we're going to do this. We are going to, so this is 16 colors. Yeah, we're going to come down here. And if it's 9 or more, we're going to get a new key. Otherwise, we're going to clear the screen and then jump to get a key. The difference being, though, we're going to modify Pt8 here. So let's get the right value into Pt8. So we're going to move AX down there. I think the first digit is the background color. You know, let's change the second digit. It'll be easier. We're going to move into BH AL. I wonder if we can just do plus 70 hex and have the assembler do this math for us. This is just a number, right? This is going to be 31 plus 7. I'm sorry, 7D. So, but we need it for the comparing to 9. You know what? Forget it. We're going to do it the easy way. BH, so we're going to just add to this 70 hex. There we go. So now when I hit keys, it should be like 1. So that 71, by hitting 1, we loaded 0, 2, 3, 4, 5. Oh, the cursor is changing color. Oh, it's clearing the screen. So that erased the 1 is black. 2, so, oh, you know, we're off by 1 as well. We're changing the foreground color, and I can see a change, but, you know, you gotta look at the cursor. That's a terrible way to go through life, so let's go bold. We can use keys 1 through 8 to generate 0 through 7. We're gonna shift left. Was it LSL? The logical shift in this? Just SHL. BH by 4. So now that we're doing that, so let's keep the foreground color black. Actually, no. I'm going to assume that F is going to be white because 0 was black. So let's find out, shall we? So we're going to read in the character, which is going to be 0 to 8, and then we'll do this. And then later we can add 8 to it here and check all the colors. Now we could probably just Google the, you know, because these are probably it's probably the ANSI color palette. But, you know, sometimes it's fun to experiment. Yeah, let's see. So now I should change the background. This should make it black, and it did. And then this should make it back to that gray color. Nope. Oh, this should be the gray color. There we go. 0 is black. 1 is blue, which is the same color that the text was. 2 green. 3 teal. Cyan, maybe. Red, brown, orange, purple. And then that gray. The gray is in bed. I can see why they went with the gray for the background. Let's look at our top color choices. This guy to 1. Like this guy is 0. Okay, so now, so this will be, did I make that 1? Yeah, that should be 8. It's getting late. Okay, so now then, this should be color 8. It's black. Whoa, these are the same colors. That's suspicious, eh? 80, I'm adding it to BH. That was interesting. We could look up the colors. Take this guy back to 7. We can do all of this, which is the right way to clear the screen. Isn't to clear the screen though. Move cursor to top of the screen. BH, AH needs to be different. DX, different from here. We're going to keep it because it is faster. It's just probably a lot more code. Oh, I didn't end up actually using that much more. Oh, no, we used like another 16 bytes. Because we went from like here-ish to here-ish. Unless we went from... Yeah, because we were almost under 100 before. Which makes sense, because these are what, like 8 instructions? And so it's probably these 7 instructions are 2 bytes each. That's fine. But we can pick a fun color pattern. So let's assume this is an ANSI color palette and see if that means anything to anybody. Color codes. There we go. Colors. So black was the first one. I do think it was... Oh yeah, here we go. VGA. So this is just the bright versions of these. That's probably why it looked the same. It was probably ever so slightly different. That's weird. There's not like a pure red. There's a dark red and redder than red. We could do bright green on black. Get a real retro look out of it. So let's see. Huh, interesting. I just assumed that these numbers would go from like 0 to, you know, 16. These are 0 to 15. These go to 0 to 15 and are the same colors. So that works out. Okay. So, oh, there's a yellow in there. Should probably check to see if that yellow really exists. But, so let's do bright green 10, which is A, on 0. So background, black, foreground, green, which was 10. That's 0A. Ooh, yeah, that's some classic computer there. I'm nostalgic as I'll get out for that. But I think, no, we're going to leave it that way. I think I'm going to put a comment here, though. Say what our color options are. That way, if I ever want to change this again, I can. So these color names match these color names. So it's black, red, green, yellow. Oh boy, that's their idea of yellow. We're calling that brown. I mean, right, like, I don't know a universe where that isn't brown. That's yellow. And these colors aren't the colors we're looking at. These are the colors we're looking at. I could put their hex values in there. Yeah, sure. It'll look reasonable. We're gonna go across and then down. So that's all zeros. And the next one is this dark red, which is half intensity red. And this next one is half intensity green, you bet it. And then the fourth one is, I mean, it's half intensity blue. Oh no. This one's half intensity blue. Yep. We got this yellow first. Half intensity yellow. Now, what is next? Oh, half intensity blue. Half intensity magenta. Half intensity cyan. Better believe it. So this was half intensity magenta. No green. And then half intensity cyan, which is no red. And then gray. Or half intensity white. No. That one's half intensity gray. This is like slightly. This one's slightly brighter than this one. So it's C zeros. So we'll go with C zeros. Conceptual thing. And I think these colors are the same, they're just the brighter versions, right? So red, red, green, green, full intensity yellow, full intensity blue, magenta, cyan, white. Okay, so yeah. And that's our colors. So what the way I want this to look is I want this to be like 0 plus. And this one's 4 plus, 8 plus. And this one is 12 plus, but we're going to do that in hex so that it's C plus. We'll go over the second to last character. 0, 1, 2, 3. Let's make that a capital C. There we go. Now we have a markdown table. But there we go. Now we got all of our colors. Bright green. So we have our full program. Do one more test, then a commit, and I think we're done. Make clean all. Make. Okay, so we're still at that 115 hex bytes. There it goes. So now I can DD this onto I have a floppy drive on this computer. So I could DD this onto a floppy or onto a USB stick and then reboot and test it. This bootloader does not support any sort of streaming, so you guys couldn't see it. But as it only supports rolling dice, I think we have something we can be kind of proud of here. And it certainly has the same look of my original. The code's a little cleaner. Obviously it runs on this new compiler. It no longer requires any DOS system calls. If I changed anything, I'd probably modify it so that I could make it also build an original COM file. If it's a COM file, we don't need this boot sector magic at the end, but conversely, it doesn't hurt to just leave it in there. And we need to change our org from 7C00 hex to 100 hex. We want to be able to quit the program then if we're running from DOS as well. So the way we do that is we'd want to change this to, rather than being a jump, so put an int 20 here. Well, if we're going to have that commented out, I'm going to have right after this guy commented out, or right before him commented out. Actually, let's see if we can go over here and open the original. Dice. Awesome. It was when we hit quit. Yeah, it was just an int 20h. So we can just put an int 20h. Yeah, so we could build the original DOS.com file pretty easily if we needed to. And all of this should work exactly the same in there. The BIOS calls are also available. I mean, we could have had it jump forever to main and be like, well, once you started this program, your only option is to run it forever. Cool. Okay. We're a little bigger than it was before, right? It was 304 before. We could, oh no, we can count the bits, right? We counted them. There was 115 hex. What does that work out to? So it's 277. So we actually shrunk this thing. It was 304 before, so we cut, you know, almost 30 bytes. It has a lot more checking on functionality, on input, and it has the full implementation of the writing the numbers and writing the strings. Let's commit it. Just to review the changes we made here. We created an init at the beginning, which has a main loop in it, which just calls our dice program. We now clear the screen using function 60 versus setting the mode to text mode. We got rid of that label and refactored this main chunk of code to first check the text options and then use a lookup table for getting the which die to roll. And we use now all local symbols where we can. So let's commit this. Finished. Cleanups. Let's make this multiple lines. Added range check on inputs. Added text colors. So that's the end of that. So we can do one more diff here with kdiff3. Let's see. Is there anything that it can still recognize? It's trying. Put these two lines with the dice symbol next to them. Then it sees that we have an int16 here. There's only one call to read a character in this whole program. So it knows that's the same. Then it's like, nope, nope, nope. Oh, we divided by bx in here. Are those even the same bx's? Yeah, that's the same. That's the same division by bx. We just, you know, use max rand, whereas they use 00f. So it's that's pretty close. The seed is still a data word equal to 1. Could have probably left die up there, and that probably would have helped it. But total is still 0. It didn't quite catch that. Dashes. The dashes is basically the same. Oh, no, we got lots of little changes. And then this program, I think, ended there. Yeah. So, you know, even though if you've sat through this, you've seen how much of this is still basically the same as what it was. Very little of the code wasn't changed. But I think we have something much better now. So I hope you enjoyed this video. If you stayed till the end, congrats. This is the end of the series on this assembly dice roller program. We may come back to it in the future for a couple tweaks that have occurred to me since this was originally recorded. Eventually, I'd like to investigate porting the similar assembly Pong game I have, but next time I think we will look at something completely different. Post any questions you have in the comments below, subscribe or come back often to catch the next video, or come follow me on Github or hackaday.io. Have fun out there and keep on crafting.